Wonderful. I also have my colleague Eric Hoagland on the line, who's going to take the second half of this presentation. So you'll hear a little bit about a different science discipline. When you think about science and utilization on and around the moon, you don't think of human research too much. But our whole charge is to make sure the humans not only survive on these missions, but thrive. And we haven't been doing the strategic planning in a silo. We have had the opportunity to collaborate with our science mission directorate colleagues, which is wonderful, not just because they're great people, but also it helps inform us of any potential tasks or activities that the crew would do on these missions, so that if we need to modify our research plans, we can do so. So next slide. I'm going to give a little bit of an overview of the human research program, because again, it's sometimes not in the forefront of science planning for Artemis. But again, our whole intent is to reduce risks to human health and performance to explore beyond LEO. And how we do that on the next slide. So if the ultimate goal is sending humans to Mars, those missions are going to have inherent risks in them to the crew. And we categorize the risks into the 5 hazards of human spaceflight. You see the circular icons on the arrow on the right. You'll also see it in a few charts coming up here. But these hazards for a Mars mission are going to be at maximum intensity of what the crew has ever experienced to any mission to come before. So how we figure out how the crews will adapt on these missions and what countermeasures we have to have in place, or what standards or requirements, we basically work backwards. So on the next slide, looking at all of the hazards and risks for a Mars mission, we use any platform we have to basically either simulate those hazards and risks or where the hazards and risks are inherently present. So we do a lot of research on ground studies on Earth. We do research on the International Space Station, soon commercial LEO partners, and we will be doing research on Artemis missions. So again, we know how humans react and live in a 1G environment. We have considerable data in 0G, and soon we'll get that partial gravity data. And so where HRP and where our work kind of fits in the whole standards flow, that's in the graphic in the bottom. So again, we're part of this bigger picture. And on the next slide, just our general philosophy to Artemis missions is knowing they're going to be very different than space station missions. You know, only once a year, limited crew time, reduced, up mass and return mass. We say that the mission is our science. Basically, to see how the crews perform in this new mission is going to give us a wealth of data. We also don't want to, we're trying to be as unobtrusive and as non-invasive as we can. So talking about Artemis 3 in specific, next slide, please. So why is Artemis so important to us? Again, looking at those 5 hazards, these missions will be very different. Smaller vehicles, so the crew will be more isolated and confined. They're going to be farther from Earth, so longer comm delay, limited resupply. But the 2 big ones are that partial gravity environment. So when humans transition gravitational fields, some odd things happen to our physiology. Some of those changes or adaptations occur within minutes or hours, and others take days or weeks. And so we really don't have a lot of data in a partial gravity environment. So looking at those changes will be really helpful to get us to Mars. And also going outside the Van Allen belts will give us information on deep space ionizing radiation. So how do we get the studies we want to do? HRP is an applied research program. So we get our marching orders from the Office of the Chief Health Medical Officer, who sets the risks for these different missions. And so we do our part to do research to reduce the risks set by OCHMO. And we like to say that since we're all very different, and if we all went into space, we would all adapt a little bit differently to those missions. So I can't say how one person reacts is how someone else is going to react. So what we do, every study will have a minimum subject count to make sure that our recommendations kind of, they embody what a typical astronaut response. So we want to get started on collecting data as soon as possible. And that N it's different for every study, but very general rule of thumb is about 10 subjects. Crew subjects will get you about 80% confidence in your data. So we follow the crew through the whole mission. Again, we want to take data points throughout the mission, even starting pre-flight to get the baseline, and throughout the mission to look at how the different environments, how the different gravity fields really are affecting physiological systems, psychological systems, team performance, all of that. And then we also take data post-flight. Another things we're doing is we're really trying to work with our medical operation counterparts on these missions. So where we can identify, one medical device that will provide data for research and operations, that's what we want to do. Okay, I think I have one more slide before I hand it off to Eric. So again, our overall objectives for these early missions is look at the gravitational transitions on human systems, look at the deep space ionizing radiation environment, and just general characteristics of human system adaptation. So I'm going to hand that over to Eric. He's going to talk a little bit about our Artemis 3 study candidates and then hone in on one specific study.
Thank you, Laurie. If you can go to the next slide. So as Laurie noted, these are our study candidates for Artemis 3. We are well aware of the limitations in terms of mass, volume, crew time, all the aspects of things that you need to perform utilization on these missions. So as Laurie noted, we are in applied research. So all these for this mission specifically fall under that directed research category. We have prioritized what we want to do based, as you see on the left there, based on things that are non-recoverable. And I'm going to do a quick spotlight on that top study in the following slides, as it's what we deem something that we can't get any other time in the mission. So lunar landing and egress, we want to do a certain number of measures as the crew is transitioning from that microgravity to the 1.6G of the lunar environment, in order to capture some of that data, which will enable us to provide some input to future missions and hopefully enable things like longer EVAs, faster EVAs, getting out the door sooner as we have a better understanding of the physiological responses. As you can see going down that list, we also have a number of other studies we're looking to do. Artemis Standard Measures, as currently listed, is looking to do some just basic research of parameters that multiple studies would be interested in. We're interested in lunar descent and ascent injury, so making sure we can gather the data to inform how the crew is responding to that dynamic phase of flight having to do with that ascent and descent. And then looking at other systems such as the immune system and our fine motor skills. As Laurie also noted, we have a series of pre- and post-flight experiments that we're also looking to do to gather that response of the crew member to the mission and to that scenario, so we can have a better informed response from our medical team on, hey, as they see perturbations to the crew's physiology upon return or in mission, what does it mean and what's causing it? If you go to the next slide, please. As I noted, I'm just going to go through a quick spotlight of the lunar landing and egress study. Move on to the next one, please. So why are we doing this study? So this study has a background of you're looking at transitioning from weightless to the gravity environment impacts your sensory motor function, something that's going to be very important for the crew to be able to do, or something they're going to rely on to perform a lot of these EVA tasks that our folks over and our friends over in SMD or tech demos for STMD are looking to do. So we're trying to understand exactly what that impact is to the sensory motor system. And the potential side impact of the cardiovascular deconditioning. We do know from research that we've done already on ISS and on the surface of the Earth that cardiovascular deconditioning in weightlessness can exacerbate the postural disorientation. So we want to make sure we have start developing this data set to have a better understanding of really what is the cause of that and what can we do to counteract it. One of the pieces there in the operational relevance section is using this data to characterize the response in order to enable countermeasures. What can we do pre-flight and training? What can we do in flight during the transit to minimize or mitigate these impacts to enable a crew to get out and be successful as early as possible for as long as possible, right? Apollo was a much shorter mission, a single EVA as they land and then they came back. So we're looking now to do 6-7 day missions with 4 EVAs over that time. Having an understanding of the physiological impacts and the ability to make sure the crew members are safe as they move forward is going to be an important piece as we move on to the later Artemis missions. So again, that's a very high level overview. If you go to the next slide, I think this is our wrap up slide. I want to thank everyone for the opportunity to have a pitch here today, and look forward to answering any questions anybody might have.